Hi students, welcome to my lectures on mechanical unit operations. In today's lecture, we are going to know about different kinds of Reynolds numbers. Yes, there are different Reynolds numbers that exist, and every Reynolds number measures the ratio of inertial forces to the viscous forces. But even though the Reynolds number is the same, there are different situations that comes in the chemical engineering. So for different different situations, there are different kinds of Reynolds numbers are in use. Okay, that is why when you talk about the Reynolds number, we talk about the inertial forces to viscous forces. But even though the definition is the same, but the way of measuring and calculating are different for different situations. Today we are going to see 4 different situations. One is pipe. When the fluid is passing through the pipe, what kind of Reynolds number we use? When the particle is settling in a liquid or any particle is settling in a air, then we use the particle Reynolds number. When there is a packed bed is there, the Reynolds number for the packed bed is going to be different. And the 4th situation is agitation and mixing. When some agitator is revolving around and there is a different Reynolds number, that is we have to estimate. So for every situation we are going to see 4 things. One is situation, second is formula to use, and third in what is its range, and fourth is objective. Okay, why we are measuring the Reynolds number for that particular situation with a small example also. So let us go to the first case. The one is called pipe Reynolds number. This kind of Reynolds number you have to estimate when there is a flow is happening through a conduit, as a pipe or rectangular conduits or anything. So what is the pipe Reynolds number definition? dV rho by mu. What is d in the case is called diameter of the pipe. Okay, Vf is the velocity of the fluid that is flowing inside the pipe. Rho f is the density of the fluid and mu f is the viscosity of the fluid. So what is the range? If smooth pipe less than 2300 terms to be in a laminar flow, and transition region which we talk about is 2300 to 4000, which were a transition, and greater than the 4000 if you get, it is called the turbulent flow. These are the typical people use, and that because for the other situation, like if it is a rough pipe or the geometry of the shape of the pipe is different, like say a square conduit or rectangular conduit, so they for different situations you get the different graphs. Okay, for this is simply for the pipe. Along with the other situations you have to go for the graph. What is the objective of the graph is to calculate the friction factor. So there is always the graph exists. On y-axis you get the friction factor, on x-axis you get the Reynolds number. Once you know the Reynolds number, from this graph, whether it is a rough geometry or smooth geometry, you can draw a straight line. Wherever it touches the graph, calculate the friction factor. Then what is the advantage of friction factor? Simple. If you know the friction factor, you can measure the pressure drop. Once you know how much pressure drop is happening inside the pipe, you can design the pumping required. That means what kind of capacity of the pump you have to use for that particular situation, that for that particular fluid you can able to estimate. This is the use of pipe Reynolds number. Let us go to the second case, particle Reynolds number. When a particle is moving inside the fluid, so in such cases that we should not use the pipe Reynolds number, we should take the particle Reynolds number. If Vp is the diameter, velocity of the particle, density rho f is the density of the fluid, mu f is the viscosity of the fluid, and dp is the diameter of the particle. If you put everything inside this formula, dp here, the difference between pipe Reynolds number and the particle Reynolds number is, here we have to take the diameter of the particle, not the diameter of the pipe. So keep it in mind. Vp is the velocity of the particle here. Here the V is velocity of the flow. Okay. So dp v rho f by mu is the particle Reynolds number. What is the range? When particle Reynolds number is less than 1, typically people say, now instead of people saying laminar flow, people say Stokes law regime. That means if the particle Reynolds number is less than 1, you are under Stokes law. When the particle Reynolds number is between 1000 to 2 lakh, then it comes under Newton's law regime. Okay, typically once you go further, you will get to understand this. And what about the intermediate region? Normally there is always a graph exists. Here you calculate the friction factor, here you calculate the drag coefficient. You get the drag, once you know the Reynolds number from this graph, and the graph will be different for different shapes and sizes. Okay, once you know the Reynolds number, you can calculate the CT. And what is the objective? If you know the CD, drag coefficient, you can estimate what is the terminal settling velocities of the particle. That means it typically in sedimentation or fluidization, these are the situations people estimate the drag coefficients. Once you know the drag coefficient, you can estimate what kind of velocities are there existing inside, of the flows, particles is moving inside the fluids. Example, if you know the dP, here also we have done the example. If you know the diameter of the pipe, velocity of the flow, density, viscosity, you can calculate the Reynolds number. Here also diameter of the particle, velocity of the particle, density of the fluid, viscosity of the fluid, you get the particle Reynolds number. Okay. Third situation, which is called packed bed Reynolds number. Typically in chemical reaction engineering also, you get to see the packed bed reactors. In fluidization chapters also, you get to see this kind of packed beds. In these kind of situations, we have to go for packed bed Reynolds numbers. Typically in the other books, it's called the modified particle Reynolds number. So this is how the looks like. If there is a packed bed, see, it's a bed of the particles are there in which some fluid is flowing through, which is having the density of rho f and viscosity of mu f, and dP is the diameter of the particle that is there existing inside this packed bed. And if you know everything, what is the packed bed Reynolds number? dP V0 rho f by mu f divided by 1 minus epsilon. Epsilon means what is the porosities. That means what are the spaces between the particles. If you count all the spaces in the particles, compare, and you can calculate the porosity inside, spaces, and if you know the porosity, you have to divide with 1 minus epsilon. What is V0? Velocity. Which velocity? The velocity, which is typically is called superficial velocity or empty tower velocity. That means you can see here the bed of the particles are there, here the empty space is there. So when you measure the velocity here, which is not occupied the particles, it is called empty tower velocity or superficial velocity. Once you know the velocity, because it is impractical to measure the velocity, because the velocity between the particles is very high, because there are less space that between the two particles, the velocity is very fast between the two particles when the fluid is passing through between these particles. Okay, once you come here, here it is called empty tower velocity, because the velocity will be stabilized here, and once you measure the velocity at this location, which is not occupied by the particles, that is called the empty tower velocity. So once you know diameter of the particle, empty tower velocity, density of the fluid, viscosity of the fluid divided by 1 minus porosity, that means spaces porosity. So once you know this, you can calculate the bed Reynolds number. What is the range? When it is less than 10, it is called laminar, typically say in this kind of bed Reynolds number. When it is greater than 1000, it's called a turbulent. So there are graphs to find out the intermediate regimes. What is the objective? Okay, once if you ask me what is the objective, calculate. If you know the Reynolds number, and we know what kind of, because ultimately the objective is to measure how much pressure drop I can expect for this kind of systems, because typically in fluidizations or in filtration chapters, you have to estimate what is the pressure that is required. Okay, once you know what kind of regime you are in, you can calculate the delta P. How you are going to calculate the delta P? Using different empirical equations like Blake-Kozny equation, typically used for the laminar flow. You can calculate delta B using Burke-Plummer equation, typically applied for the turbulent flow. And delta P, which using Ergun equation, if you have entire region, because the Ergun equation applicable for even laminar flow, transition flow, and turbulent flow. So use, if you know the Reynolds number, you can estimate which regime you are in. Depending upon that, you can estimate delta P using any one of these equations. Simply example, what is the diameter? Diameter of the particle is 0.1, superficial velocity is equal to 0.5 meter per second, and rho f is the density, 1 kg per meter cube. Viscosity 0.01 into 10 power minus. Typically fluidization of sand using air, if you do, in such situations the densities are very low. If you are using air as a fluid, the densities are very low here, because here is 1000 kg per meter cube, here is 1 kg per meter, because here the water is used, here the air is used in this bed. Okay, epsilon is the porosity is equal to 0.3. If you put everything in this equation, you get bed Reynolds number is 7142. And the final situation, which is called agitation. In agitators, there is a different Reynolds number people use. And if you see, this is the agitator, and this is agitation tank in which mixing happens. And this is the agitator. This is the length of the the diameter of the agitator is di, and n is the speed per second how many rotations the impeller is going to revolve. Okay, da is the diameter of the impeller. Okay, this is a tank in which some liquid is getting mixed. In such cases, the agitation Reynolds number, if you use di square into n into rho f by mu f. Why is di? This is the diameter of this impeller. What is n? Rotations per second. And what is rho f? Density of the fluid inside this agitator, and mu f is a viscosity inside this or the fluid. Once you know everything together, you can estimate what is the agitator Reynolds number. Range. If Reynolds number is less than 10, go for the viscous. Typically laminar flow happens inside the agitator. Typically it's a viscous flow that dominates inside the system. When Reynolds number is greater than the 10.4, it comes to the turbulent flow. What is objective? Okay, here I can calculate the friction factor, here I can calculate the drag coefficient, here I can calculate the power number. Okay, because there is a relationship between the Reynolds number and the power number. Once you know the Reynolds number, you can estimate the power number. What is the use of power number in the agitation situations is, once you know the power number, you can calculate the power that is utilized and power of the impeller that is required to mix or agitate the systems. So once you know the Reynolds number, you know the power number. You know the power number, you know the power requirement for the agitators. Simple example, if I know the diameter of the impeller, what is the rotations per second, what is the viscosity, and if I know the density, put everything in this equation, estimate the Reynolds, agitator Reynolds numbers. I hope you have learned different Reynolds numbers for different kind of situations, because my students always tend to find that only they are in a situation that there is only one Reynolds number exists, but that is not the case. There are different Reynolds number existing for different case. Everything is doing the same, inertial forces by viscous forces only, but the way of measuring is the different for different situations. Thank you. I'll come back with a different video.